I'll be talking about EOS, which is efficient private delegation of zkSNARK provers, and this is joint work with some excellent co-authors, Alessandro, Pratyush, and Yinuo. So in many cryptographic applications, one party has some private input and wants to convince another party that this input satisfies some property. So to give a concrete example, here we have a prover and a verifier. Let's say they have access to some public hash value X, and the prover additionally knows some witness W that they want to convince the verifier is a valid pre-image for X. And this problem actually comes up in some real-world applications where you have, let's say, Merkle tree commitments over private data. And one tool that we can use to solve this problem is zkSNARKs. So the prover can generate a zkSNARK proof, give it to the verifier who can check this proof and be convinced that the statement is true. And zkSNARKs have several nice properties. So the proof is super short. The verifier runtime is also very short, which is why I've represented it as a mobile phone here. But most crucially to our work, this proof is zero knowledge, which means that the verifier learns nothing about this witness except that the condition holds true. And these properties have made zkSNARKs very critical components of both theoretical works as well as actual deployed protocols. And their popularity has led many people to explore different ways to construct them with differing trade-offs. But one common theme in all of these constructions is that proving is still very slow. So if I take this example here, let's say this witness is 50 kilobytes long, then even using the state-of-the-art zkSNARK for this problem, which was actually presented here yesterday, the runtime of the prover is going to be 1 minute, while just computing this hash locally would be on the order of milliseconds to even microseconds. Okay. So this is a big problem, and in general, there's oftentimes orders of magnitude difference between just checking a property locally and using a zkSNARK to prove that that property is correct. And to make matters even worse, in many applications of interest, the prover is not a powerful machine, but is also a resource-constrained device, such as a mobile phone. And so this very much restricts how we use zkSNARKs in practice because we either have to prove small instances, simple properties, or we have to have very powerful machines. And so in this work, what we're interested in doing is making proving practical for large instances, hard problems, and especially for resource-constrained devices. And one way that we might be able to do that is to delegate proving. So we can have our prover send its witness to a set of more powerful cloud machines, and they can generate the zkSNARK proof for us and send it back. And in fact, prior work did just this and showed you can speed up proving significantly. But there's a big problem here, in that now we're leaking this private witness to these workers who might be malicious. So in the setting where this witness is very sensitive, this is not an acceptable solution. So our goal is to do delegation, but with privacy. So we have the same picture as before, but now we want to provide our witness in some encrypted or obfuscated form. And we have kind of two goals for our protocol. Our first goal is efficiency. Delegation should be faster than local proving. And our second goal is privacy. The witness should remain hidden from the workers as long as one of these workers is honest. And in our work, we present a system called EOS, which achieves this definition of private delegation of algebraic zkSNARK provers in the presence of n-1 malicious workers. And this term algebraic here captures many state-of-the-art zkSNARKs, such as Plonk, Halo2, Marlin, etc. Compared to local proving, running EOS on a mobile phone is 26 times faster and uses 256 times less memory. And we have a number of technical contributions to get there. Today I'll have time to talk about a few of them. So we'll start by discussing how we build efficient circuit for zkSNARK provers. I'll then talk about how the setting of delegation can be used to speed up MPC, and then we'll present some new lightweight techniques for malicious security. And the starting point for all of these things is multi-party computation, or MPC. And MPC allows multiple parties to compute a function f over their private inputs. And in this work, we're interested in n-1 malicious security, which informally states that privacy and correctness of our computation holds if at least one party is honest. Now, what we would like is for our workers to use MPC to compute the zkSNARK prover. But doing this naively doesn't work because generic MPC is expensive. So while we would meet kind of our correctness goals, we wouldn't reach our efficiency goals. And the rest of the talk will be focusing on how we specialize this MPC to actually make this proving practical. So the MPC protocol that we'll be using today is called speeds. And at a very high level, in speeds, you first express your function as an arithmetic circuit, and then all parties execute this circuit gate by gate using some special protocol for each gate. And immediately we run into some issues because the circuit used to represent the zkSNARK prover is very large. And intuitively, this is because you need to support things such as polynomial arithmetic, group operations, and random oracle calls. And all of these things, or naive representations of these operations, result in huge blowups in the circuit. So to get around this, our idea is to extend the circuit model. And this is similar to some prior work. So we're going to add gates for both group operations as well as random oracle calls, and then we also contribute new efficient subcircuits for polynomial arithmetic within this extended circuit model. And by doing this, we end up with a circuit for a zkSNARK prover that is efficient. But we can still do better. And to do better, we're going to use the asymmetric threat model that exists in delegation. So what I mean by that is normally in MPC, you have n parties computing, and any of those parties can be malicious. However, in the setting of delegation, we have this prover, and this prover is always honest and knows the witness. So our idea is let's use this weaker prover to assist the MPC. And now the difficult part here is figuring out where we want to use the prover. So we don't want either the communication or the prover's weak computation to be bottlenecks in our protocol. And when we look at the circuit for the zkSNARK prover, what we notice is that both computing multiplications as well as random oracle gates is incredibly expensive in MPC. It requires some public key cryptography, while it's very cheap to compute in plain text. So our basic idea is we take our zkSNARK circuit, we kind of mark out subcircuits that contain these gates, and when workers reach these gates, they're going to share the input wires with the prover. The prover will execute the subcircuit in plain text, and then it will share the output wires back with the workers who will continue executing the circuit normally. And so by doing this, we can save significant amounts of effort in our multi-party computation while having only a very small computational overhead from the prover's perspective. And the final way that we speed things up is in how we achieve malicious security. So standard techniques for achieving malicious security incur a large overhead. To get around this, what we notice is that the thing we're generating, a zkSNARK, has some very nice properties. And in particular, zkSNARKs are error detecting, which means that an incorrectly generated proof will fail to verify with high probability. And so our idea here is let's use this improperty of the zkSNARK to reduce the overhead of achieving malicious security. And the high-level idea here is fairly simple. We're just going to have the prover actually verify the proof when it gets it back. And we have this guarantee that if the worker has deviated from the honest protocol, then this end proof will fail to verify. And there's a bit more work you have to do here. You have to tweak the MPC in a couple of different ways, and you have to adjust how you go about the security proof. But in fact, this idea does end up working. And the cool thing is, because verification for zkSNARKs is so lightweight, we essentially get malicious security for free in our delegation protocols. Now, there is a caveat here. If you notice in the model I have, the workers do not see this resulting proof. And in many applications, this is true. However, there are some applications where this proof is publicized, such as in blockchain. And in these situations, the workers might see the proof. And here things get a bit more complicated because something called a selective failure attack becomes possible. And this attack can leak one bit of the witness. So to get around this, we use kind of a similar technique where we're going to use additional properties of algebraic zkSNARKs to eliminate these attacks. And as before, because we're utilizing the structure of the thing we're building versus trying to do this generically, we end up with a technique that's actually very lightweight. Now, you'll notice there's an asterisk here, and I want to thank Xiao Wang from Northwestern, who very helpfully pointed out that there's actually one more selective failure attack that these two techniques do not stop. However, the selective failure attack applies to only a very small subset of instances that you might choose to prove, many of which aren't in actual applications. And so as long as your circuit kind of doesn't fall into this vulnerable subset, then you still have malicious security. Okay, so those are our technical contributions. We implemented EOS as a Rust library in the ARCS ecosystem, and we ran some experiments. So we specifically evaluated the Marlin zkSNARK, and in our experiments, we used 2 workers on either side of the US. And the first thing we want to show is how EOS compares to local proving. And we did this for 2 different types of provers. So we have an R4 AWS instance, and this is meant to kind of emulate a standard laptop, as well as a Pixel 4a mobile phone. And what we see is that for the laptop with a strong internet connection, EOS performs 9 times faster than local proving. If we restrict our bandwidth a little bit, then we get a 6x speedup. And then when we move to the mobile phone, we get this 26x improvement that I mentioned earlier. And for all of these provers, EOS reduces the memory overhead by 256 times, which means that we can prove much larger instances than we could before. So if we compare EOS to other existing techniques to do the same thing, we can see that EOS performs 8 times better. And just to give some context here, this work by Ozdemir and Bonnet considers a slightly different setting where a group of workers collaboratively build a zkSNARK. So in particular, they don't have a prover that can assist the computation. They use standard techniques to get malicious security. And there's a few other optimizations that we have in the paper that they don't have. So this is where this 8x number comes from. And finally, if we consider the setting of insecure delegation, where I just give my witness in plain text to a worker, and they generate the proof for me and send it back, we can see that for a large enough instance size, EOS is only 10% slower. And you'll know this isn't a perfect comparison, because in EOS you have to run multiple servers versus one. But let's fix a constraint size, like let's say 2 to the 20. What we can see is that running this extra server only costs 3 cents on AWS. And so one way of seeing this is that using EOS, we can go from insecure delegation to private delegation for the cost of 3 cents and 10% increased latency, which demonstrates that our protocols are both cost efficient and practically performant. And that's all I have. The paper and code can be found here. There's an updated version that will be coming soon to ePrint, and I'm happy to take any questions.